So the global properties of continuous functions are very predictable if you get the idea of the continuity. So we don't allow anything bad happen to the graph of the function. So that's the interpretation of the function. But you certainly can think about things on a bigger scale, and the curves are good. That's because we're studying functions of one variable for the time being. So one variable, but you can think about the setting, more complex settings. For example, this curve over there on the line does not have to be the graph of a function necessarily like this. It could be a trace motion on the plane, in space, in a multidimensional space. All of these are possibilities, and that's what you expect the graph to look like, to be a continuous curve with no breaks, no teleportations, and so on. Similarly, function might have more than one variable, and then things really become more complicated because the graph is then becomes a surface. And once again, you have only two variables, and you have a surface as your graph. And so that has to wait until like calculus 2 or 3. But it's a good idea to remember that this is just the very beginning. So functions of more than one variable produce surfaces or high dimensional objects, and it goes beyond our ability to visualize, and that's why it's important to learn what's going on with this level, when we can still see it almost either drawn on the piece of paper, or it is there's some kind of analog of what's going on in describing what's going on with in terms of motion, for example. Okay. Surfaces also, you can imagine that does this surface has a cliff? Okay, so maybe something complicated. So the basic statements about there are three main theorems about continuous functions. Global properties, meaning why we speak of global properties, because local properties is the continuity is a local property. Look at the picture over here. So that's the local property. The continuity is a local property. Is there or is there not a cut through this point in the curve? Okay, and then you examine every single one of them. Now, suppose we assume that there is no there are no cuts at any point, then we say so if f is continuous at x, for all x, each x, every x in the interval of any kind, let's say I, then we say then f is called continuous on I, continuous on I. So never forget that the original definition is about continuity at a point. That's so verifying limits that over the point one point at a time. And then if we have verified it, then we can speak of a function continuous on an interval. Okay, no matter what that interval is. And so then we know that polynomial functions are continuous throughout the real line, and rational functions are continuous on its domain. So let me just state it. So polynomials are continuous on negative infinity, infinity. Firstly. Secondly, rational functions are continuous on their domains. So domain of rational functions where your denominator is not equal to 0, so you don't end up dividing by 0. So you say, well, that's the point in the domain. Elsewhere, not only you don't divide by 0, then everything is really fine because the function is continuous. So you can certainly continue this way, but what are the conclusions that we can draw about these facts? And number one, let me start with the intermediate value theorem. So we want to say that the relation between the continuity between the continuity of the input variable and the continuity of the change of the output variable is direct. So it goes through the continuous function, and if the function is continuous, then we're not skipping values. So that's the idea, that no skipping of values of y this time. Okay, this is how it is stated. So suppose f is continuous on an interval AB. Okay, and then we take the endpoints of the interval and look at the value of the function at these two endpoints, and then see what's happening in between. Okay, and there won't be any skipping. There won't be any skipping of the value. So, well, let me not plot the graph of the function. Let me plot the only two values that we know for sure are there. This is A, and this is B. Okay, then this is f of b, and this is f of a. Okay, so intentionally I do not plot the graph of the function here. It's because the intuition is there anyway. We know that the graph is supposed to look like a curve, and so which means that you can say roughly that we're not going to be skipping any value. So that's why I'm plotting the graph of the function without the function itself. So I'm only plotting 2 points. So these are the 2 points on the graph of the function. Okay, so then the function is defined and continues on this interval between a and b. So x runs from x to b, no skipping. So there are no skipping on the x-axis between a and b. Okay. What we wanted to conclude is that there is no skipping on the y-axis as well. So no skipping here either. Okay. So I once again, there is no f drawn, but imagine it's here somewhere. Somehow it is plotted. We just try to. Maybe it is a nice curve. Maybe it is nasty a curve. But we do know that it is continuous, and then that's what we conclude, that there is no skipping of the values of y. Once again, the no skipping of the value of x is a given, because we know the function is defined on an interval, and after all, the input is the independent variable, which means that we can control it. And so if we want to run from a to b, we can. But can we run now from f of a to f of b? And the answer is yes, if the function is continuous. Otherwise, there is no guarantee. Remember, that's a function like that. You see what has with a function graph looking like that, there is a missing value. There is a missing value of y. Okay, so let me just state it in mathematical terms of what we're saying here. So then, for any value of y equal, say, u, there is. So how do we know that we're not skipping? We trace our steps back. Okay, so what does it mean that the value between f of a and f of b, there is a point. Every point is there. It means that it has come from somewhere. So I pick a value of u between f of a and f of b. There is a value of u. I'm sorry, this is what I'm saying here. For any value of y equal u between f of a and f of b. Okay. We take any value, and then we're saying that it's been covered. What does it mean? It means that y, this u, comes from somewhere. It comes from some value of x within the interval. So there is, say, a c in AB such that f of c is equal to u. Okay. Let me plot it one more time. AB. Okay, then we start with the unknown u. And then what we're saying is that we're going to go backwards towards the graph. There's some graph here, okay, of our function. And then we go backwards from u, like this. No, red, green. Until we hit the graph and then go backwards, and this is how we find our value of c. Okay, so that's the meaning of it. No skipping of values on intermediate value theory means that every intermediate value between f of a and f of b is not missing. Okay. Motion, all the explanation that you can think of. So if the time is continuous, the motion is continuous, it means, and you get from f of a to f of b, it means that you have visited every single point in between. Okay, you cannot skip them. Okay, now, so read more about this in the book. In the meantime, there are two more theorems about continuous functions. Boundedness theorem. This one is simple. If f is continuous on the interval ab, then f is bounded. Bounded function means, well, first of all, this is what we call a closed bounded interval. Interval. Okay, so AB and both of the endpoints are included. That's what the brackets are about. And then but that's in the x-axis, right? That's in the x-axis. The domain is we keep it between a and b. So the graph of the function then lies between these two lines. Okay. And but then what we're saying that if the function is continuous, the function cannot go to infinity. Okay, what we're saying is that it is also bounded. Also, there is an interval. So in addition to this, there is that. Okay, and my graph is here somewhere. So graph fits into some kind of box in a rectangle. Okay, so once again, we can control the x-axis and the inputs. Okay, so that's, and we just say let it be within the interval. We generally cannot control the value of y because the function does control that. But sometimes if we know the function is continuous, at least we can draw some conclusions. The function is not going to infinity. So let's say, well, let's just it is bounded. So it's fit. It is fit between some numbers, say c and d. Okay, that's the value of y. These are on the y-axis like this. So everything fits in a box. So that's the boundedness theorem. And there is one more related theorem. Where is it? Yeah, the extreme value theorem. This is one of the most usable theorems, short term. Well, the idea is suppose the function is once again is continuous. Okay, so once again we assume suppose f is continuous on AB, is continuous on AB. Okay, then we know by the boundedness theorem, we know that the graph will fit in the box, but a lot of functions fit in the box. Okay, you can think of many discontinuous functions that fit in the box. But the continuous function have a very nice property when you try to solve, when you try to maximize or minimize the problem, the function. Okay, so to find the highest point, like this. Well, let me make it red. You're trying to find the highest point, which is a max, or the lowest point, which is the min. Okay, so generally speaking, you cannot guarantee that you can find such a point or points. For continuous functions, we claim that we can. There is always, it's like thinking about the, say, researches the elevation map of our surrounding area, and then what we're saying is there's always a point that is or points that are at the highest elevation among all of them. Okay, so that's what we're saying. But we can only guarantee that is the case when the function is continuous. Just an example when it does not work out. Well, look at this. Okay, so what's the highest value of this function? Say, suppose this is 1 and this is 2. What's the highest value of the function? No, the value, not the, what's the value is the value of the function. So the largest value, there's a largest point where the maximum point, that is the value of x, and the largest value, that is the value of y. So what's the answer? It's a trick question.
1 point.
Okay. Well, if you keep repeating 9s, you'll have 2. Remember, we already talked about. So if it's 19999, it is in fact 2. But I understand what you're saying. That you would correctly think in terms of sequences rather than at once. It's not going to be 2. It's going to be a sequence of values approaching 2, and indeed you can plot them right here like this, right? They will be approaching 2, but there is no one single value. If you are trying to tell, the question might be find the maximum value, and the answer would be, well, there is no maximum value. There is a bound being 2. The 2 is the bound, but no, there is no point where this value is attained. So if you're saying that the highest, I don't know, 1,000 feet above the sea level around Huntington is the highest point, and then you're saying, well, can you find a place for me to live 1,000 feet above there is no such place. Okay. So of course, in practical terms, the accuracy really doesn't matter. But when we do like a more theoretical stuff, then the infinite accuracy is inevitable. So that is a discontinuous function on the right. That's why it might behave this badly. It could behave even worse. It could. How about it goes to infinity like this? That's even worse. But if the function is continuous, then we are good, and then we say that in these terms, then f attains its global maximum and minimum values. In other words, there is a C in AB such that f of C is larger than or equal to f of x for all x in AB. Okay, so that's the maximum. There is a point, literally a point, that is within the interval, and the function is defined at that point and is the highest value. And then secondly, their minimum is also possible. So G in AB such that f of C is less than or equal to f of x for all x. Okay, so that's the language that, the awkward language that we use, but actually it is, what's behind it is that these two lines of text, the extreme value theorem. So then if you combine these two inequalities together, that creates a box. If you take these two together, then that is the top and bottom boxes for x. So for y, x lies between a and b. Meanwhile, y lies between f of a and f of c and f of d and f of c. Okay. Okay. So this is the box. All x's and y's. X's lie within the interval. Y also lie within the interval like this. So once again, this is AB, and then we have two more. F of D, the smallest, f of C is the largest, and my graph is then lies here somewhere inside. Okay. So it's like the previous theorem, the boundedness theorem, but with more specificity. We can actually, it's not doesn't just fit in the box, but actually you cannot do any better job, right? So it reaches point here somewhere and reaches point here somewhere, so you cannot make the vertical bounds, the lower and upper bounds of this rectangle smaller, okay? Because the graph fits perfectly in it. Okay, so as I said, these are important theorems, and we just don't have time to discuss them at length. So I have to ask you to read about this in the book. So these theorems usually come together. I don't remember the number of the section. So extreme value theorem, boundedness theorem, and the intermediate value theorem. Okay, so there might be some homework on that at some point, but at this time we'll just mention them and proceed on to the next topic, and that is asymptotes. The topic is really not complicated, but has to be you have to take a right point of view. So it's if I want to start the right way from the beginning, you just look at the function y equal 1 over x. Okay, and the function might be continuous, but this one is not continuous at 0, and it is also, there has some behavior at infinity. So that's what we care about. What we just looked at, global properties, were really the properties of the function limited to a bounded interval. So global means on an interval AB, closed bounded interval. So you can see that this is not the case. What we're looking at right now is let's just take one branch. Let's ignore the other branch. Let's just take one branch of 1 over x. This is what we're looking at. We're looking at 1 over x on the interval of 0 in plus infinity. Okay, so this is the interval we're looking at. So you can see the difference. So closed bounded interval or interval that is either or both open. So remember, this is open. That's what make interval open is that you exclude the endpoint, and also infinite. You could have one or both. This is I want to take one function, so we have both at one place. So this one is closed bounded, and this one is both open and unbounded. Okay, so with the switches is complete. We are studying the exact opposite, what we did not study in the last topic. So whatever is happening between those two extremes, these are the extremes that we are now really care about. This part and that part is what we care about. Whatever in between, just been taken care of in the previous topic. But these are the two parts that we want to take care of, and what is about patterns. So it's always about the same thing. So patterns at the ends of intervals, meaning intervals either open or infinite. In either case, there's some pattern of behavior, and sometimes they are very simple. Well, this is simple enough, but here's another example that actually is just as simple. How about this? So let's say y is equal to x squared. Then what is the pattern at infinity? And it is really not very hard to describe. But you know what's happening to y equal x squared. We can also invoke our knowledge of sequences. So x squared, what we're interested in, I underlined that branch, and assuming that it goes on and on to infinity. So we are asking ourselves, where does x squared goes? Where does x squared go as x goes to plus infinity? So x goes this way. Where does y go? Like this. Also plus infinity, right? So plus infinity like this. So that's the simplest, most typical situation. X squared is one of the simplest functions, and the behavior at infinity is very frequently is infinity, either one or the other. But as you can see with function 1 over x, the pattern might be different, and quite dramatically different. You see what's happening there with 1 over x. Again, look at this branch. So this is what's happening to x. and we're looking at what's happening to y. So x is moving from right to left. What's happening to y? It's going down, yes. So 1 over x, where does it go as x goes to, it goes to 0, right. So this should be familiar because it's not almost exactly the same thing as with sequences, except now instead of having a bunch of dots like this, we have a curve. But the idea is exactly the same. Okay, so that is when this is the case where there's a limit of a function at infinity, then we say that this is called a horizontal asymptote. So the words asymptote, so y equals 0 is the horizontal asymptote of the function. So that is how you describe it verbally, but it always comes together with the description as a limit. So 1 over x goes to 0 as x goes to infinity. Translated into human language is y equals 0 is a horizontal asymptote of 1 over x. Okay. So then for x squared, well, if asked, you just say no horizontal asymptote. Right? So you can certainly try to describe beyond the what we see here. Once again, drawing on our understanding of sequences, what's going to happen? What I only with 1 over x on right, I only underline a small piece of the graph. So what if we start moving further and further to the right? What's going to happen? With the graph.
On x squared?
Well, no, 1 over x.
It's going to get closer and closer to 0.
Yeah.
Till
what? Yeah. Okay. That is really a question. Till what? Well, imagine you have a graphic calculator. So what is going to, and you are moving the window to the right more and more.
The y value is going to get smaller and smaller.
Yeah. And keep going. They will merge. You can try it yourself. They will merge. The graph will be indistinguishable from the y-axis because it is 1 pixel wide, and when the number is small enough, it will be less than the width of a pixel, and so they will be like this. Well, which one is which? I don't know. So like this. So suppose this is my graph. So this is my x-axis, and then somewhere here as well is the graph. Okay, so at some point you still are able, they are two adjacent pixels, and then the next one they're the same pixel, inevitably. Okay, so that's the pattern. So in other words, the function flattens out to the degree that it is virtually horizontal. So not only they merge together, but well, I mean the x-axis is the straight line, so the graph becomes a straight line. So in fact, if you zoom in, then this is what you're gonna see is well, let me just to give you an example. If I have y equal 1 over x, so you wouldn't think that it has got to be necessarily the x-axis. It could be any other plus 1. So if I add plus 1 over x plus 1, so then my asymptote is y equal 1 rather than y equals 0, and but the idea is still the same. A horizontal line, and the graph of the function merges with it and becomes indistinguishable. That informal description has a very solid stuff behind it, and that's the limit. Okay, so that limit, that's why we start a limit, so that we can put things in a precise on a very good precise foundation. Okay. So these are horizontal asymptotes to begin with, and now if we go to 1 over x, it has the other branch on the which looks very similar. If you think about it, if you think about x and y like being interchangeable, x and y, and we just did it recently. Remember inverse functions, 1 over x, x, y, y, x. That doesn't really matter frequently. So the symmetry is certainly visible, right? You see 1 over x. You see the symmetry. So one branch, the other branch, you can actually put it on a piece of paper and then and they either flip or you can fold it, and it will fold on itself, right? So if you put it like this, so that you fold it diagonally, okay, and these overlap. So the behavior still is exactly the same. So let me make a little picture here. So like this, and suppose this is my graph, not like this. Okay, so, and then I could draw the diagonal, which is y equal x. This is y equal 1 over x. Okay, and then these branches, what I'm observing and we just discussed, what we observed here and discussed here, reappears here. Okay, so except the relation between x and y becomes a relation between y and x. Okay, so let me once again write up what we just discovered about what's at the bottom is y goes to 0 as x goes to plus infinity. Okay, let's try to describe what's happening at the top.
As x approaches 0.
Well, yeah, you could. I would just suggest to what's happening is x and y has been flipped, right? So let's do that. Let's do that. Take that statement at the bottom and replace x with y with x. So then it will be x goes to 0 as y goes to plus infinity. But as what you just suggested, which is certainly a better way, if you're talking about function y as function of x, then you could describe it alternatively as y goes to plus infinity as x goes to 0. So it's the same thing if you think about curves rather than functions. When it is a function, then it is x independent variable, and you have to put x at the end so that you know which one's which. X controls y, so when x goes to 0, it controls y towards plus infinity. One little thing we have to fix, and that is has some importance. What?
Plus 0.
0 plus, yes. 0 plus. So remember we talked about that a little, and then now this is you see the importance of it, because when x goes to 0, the limit simply doesn't exist, because when it is a two-sided limit, remember, the x approaches 0 from right and left, but we know what's happening on the left, something entirely different. So we have to only concentrate on one-sided limit. Okay, so from the right. And these are the main types of behavior that we have. Asymptotes, except this time it is a vertical asymptote. Is x equal 0 in this particular case. So asymptotes are straight lines. So when you are to ask to find it, the answer should be an equation of a straight line. Then there are two. We were not talking about oblique asymptotes. There are also oblique asymptotes with incline. But if we just concentrate for now on vertical and horizontal asymptotes, then the equations are very simple. Either x equals to something that's vertical, or y equal to something that is horizontal. Okay. So and that is the two main patterns that some functions exhibit. Okay. So these little pictures, these two little pictures, both of these. So 1 over x has two asymptotes, horizontal and vertical. Okay. In the meantime, y not equal to x squared does not have an asymptote. That is also to be remembered, because it is possible when there is something important about the function, you have to point out when you have it as well as when you don't. Okay, y equal x squared does not have asymptotes. It's important because so there is no, to begin with, you cannot have a long-term stabilizing behavior of the value. Okay, so you remember there's some physics in it. In fact, probably worth mentioning, another recent function that has a horizontal asymptote that is 2 to the x, or say e to the x. E to the x has an asymptote, not e to the, well, e to the x, yeah. E to the x has an asymptote right here. See? It has a horizontal asymptote. Okay, so if we take the opposite one, it will have, say, oops, 1 over x, y equal 0.5x, exponential decay. Okay, so both of them have patterns. They have asymptotes of 0, y equals 0, and they're flattening out, and that is important because there is some physics behind, or rather physical processes behind it. Either you have a radioactive decay, so every 5,000 years you lose half of the amount of that element in the plant that's dead, and then it means that eventually it will be getting closer and closer to 0 until it's almost invisible or negligible, and that's what the graph on the right is. On the other hand, it is possible that if a totally different situation when you have well, the process that is time dependent, it might be growing. It might be growing, might be constant, might be going up and down. If it is a periodic process, for example, and so that's a totally different behavior. But the point is, I guess, is that I'm talking about long-term behavior. That's the asymptote, is what's happening in long term eventually. So the eventuality is what we're talking about. So if you only, no matter how large a piece you cut, you will not technically see the asymptote. The asymptote is really recognized and demonstrated only by means of a limit. Okay, so these limits, this one specifically, is what proves that there is an asymptote, and it certainly is something that describes the dynamics into the infinity, into the end of the universe. Okay, so certainly that is a mathematical concept of infinity. Okay, and then there's a short-term, really short-term behavior. That's the vertical asymptote. What can happen to the value when some quantity, hypothetically, in a period of time that actually is small, and yet what can happen that the whole thing goes to infinity. So infinite limits. Remember, we had that with sequences as well, and that is something that usually does not happen in real life. So when you have a model and that would be okay. That's very many phenomena have this property. But if the quantity goes to infinity in finite amount of time, then probably something is wrong with your model. It's not only discontinuity, which is bad enough. So once again, if you have discontinuous model, then you probably have to rethink things about it. But this is a very specifically bad thing about it. Then some quantity becomes infinite. What is kind of quantity that in real life could becomes really infinite, not just potentially infinite, but really goes to infinity. By the end of the day, this quantity will be infinite. Well, you don't really see that in real life. The only thing is that happens with functions that have been devised specifically for that purpose. And the example 1 over x has in two infinities around 0 tangent. Tangent has vertical asymptotes. Let me quickly plot it. Remember the tangent.
Looks like sine and cosine just on the y-axis instead, doesn't it?
Well, it has asymptotes. Because remember, its cosine is in the numerator, which means that whenever cosine is equal to 0, we have the whole thing goes to infinity. Okay, so when is cosine equal to 0? No. When the angle is when it's vertical. Remember the x coordinate. So when your unit interval is vertical, that's when you have your cosine. This is if we are here, then the cosine, which is on the x-axis, is 0. So this is, and this angle is, what's the angle? Pi over 2. Okay, so at pi over 2 it has an asymptote, but then it is repeated every time, because then when you're here, it's once again a cosine is equal to 0, and so it is repeated every pi of length. So this is what it looks like. And it has two vertical asymptotes. Okay, and then it is, as I said, you repeated that at every single time. The challenge that, okay, let me plot it first. So another one like this. Oops, a red one. Okay. So the challenge is, by the way, once you look at this picture, is our recent discussion is the inverses. There is arctangent. So just since I have the graph right here, so let me ask that question: what is arctangent? Arctangent, what's the meaning of it?
X over Y.
No. No, the arctangent are just like arcsine, arccosine, arctangent. What are we talking about? Arctangent. It's the inverse. So arcsine is the inverse of sine, and so on. And the challenge with sine and cosine are both periodic functions, and as such, they are not one-to-one. This is also not one-to-one. So the only way, as we've seen, that the function is not one-to-one, and we need the inverse, what do? We cut whatever we don't like out and make the domain as small as possible in order to make the function one-to-one. How do I make this one-to-one? You see, it certainly fails the horizontal line test. So what do?
You just take the values from negative pi half to pi half.
That's right. Yeah. So this is tangent restricted to negative pi over 2. Well, it's not defined at pi over 2. Pi over 2, negative pi over 2, pi over 2, and then there is arctangent. What it will look like. Well, can you look at the orange line? So that's the restricted part of tangent, and tell me anything interesting about arctangent. Any asymptotes?
At y equals pi over 2.
Yeah.
And negative
Yeah.
pi over 2.
Yeah. So in other words, indeed, this line is x equal negative pi over 2. This is x equal pi over 2. These two are vertical asymptotes of the arctangent. I'm sorry, of tangent. Okay? When you flip and you go to the inverse, x and y have been interchanged. So what happens to the vertical things? They become horizontal and vice versa. So as a result, you have two horizontal asymptotes. So I keep calling them the same, x equal negative pi over 2. So this is my graph, piece of the graph looking like this. Okay? Okay, so that's large-scale behavior, and sometimes you can speak of things with large-scale behavior. It doesn't have to be necessarily about functions, as we just realized that it applies to a function as well as its inverse. So any kind of you can have asymptotic behavior this way, that way, going this way, or going to infinity, that to infinity. So never forget that the large-scale behavior could be simply infinite. It doesn't have to be an asymptote. So remember, never forget y equal x squared goes to infinity as x goes to infinity, plus or minus infinity, in fact. So that is just as important thing to remember, that, for example, no polynomials have asymptotes. Of any kind. So that's a fact that is convenient. So every time you have an asymptote, it means that you have some kind of special function. There is something special about that function in comparison to polynomials, which is the basic function to be dealt with. And then behaviors then they either goes to one infinity or the other infinity. Nothing else can happen. Okay. Well, polynomials degree n larger than or equal to 2. polynomial of degree 1 is a straight line. Well, then larger than or equal to 1. Okay. Yeah. Okay. So so that's the asymptotic behavior, as you can see here, that way, this way. You can approach an asymptote might be approached from both directions, or like 1OX, it might behave differently on different sides of the asymptote. So then the analysis becomes half of the time you look at rational functions, because trig function, I mean the tangent as well as the exponential function have very specific asymptotes, so we know ahead of time where they are. But certainly some transformation of the functions will create more patterns. So if, for example, if y is equal to 0 is a horizontal asymptote of y equal 2 to the x, then y equal 2 to the x plus 3, what do we know about this function?
It's asymptote would be y equals 3.
Y equals 3, yeah.
Because it's shifted upwards.
Right, everything shifts, including the asymptote. Okay, so with the horizontal, okay, let me test you. What about the vertical asymptotes? Let me take, say, tangent, and so x equal pi over 2 is a vertical asymptote of y equal tangent x. Yes, tangent x. Okay. How about x equal pi over 2 plus 1 is a vertical asymptote of what function?
Y equals,
Yeah.
in parentheses, tan x minus 1.
Wait, where are parentheses?
Tan and then parentheses x minus 1.
X minus, that's right. That's right. Okay, so minus 1 shifts the graph to the right. Okay, and asymptote shifts with it. Okay. Rational functions, let me take a quick look at rational functions. Specifically, whatever the numerator is, it's not important, but so that's why I'll just put 1 there. So x minus 1, and the typically you can assume that you know how to factor, or it has been factored for you, and then it is the factors of the denominator that will give you the asymptotes, the vertical asymptotes. So once again, the zeros, or factors, of the numerator, or I'm sorry, the denominator, give the vertical asymptotes. Okay, so all right. So can you quickly point out what the asymptotes are? What the asymptotes are here?
X cannot equal 1. X cannot equal plus or minus 3.
That exactly right. So that is just simply describing the domain, right? But then this not equal become equal to give us what?
That's the asymptote.
The asymptotes, right? So vertical asymptotes become these not equal equations of the domain. Okay. Well, that's all. That's all there is as far as vertical asymptotes are concerned. All we have to do is to look at the denominator. There's a chance that something might happen. Well, first of all, let me make sure that we realize that x squared plus 1 can never be equal to 0 as long as x is equal to 0. So that's why that factor does not contribute anything to neither the domain nor the asymptotes. So it could happen hypothetically that, say, I have x minus 1 somewhere in the numerator, and then if you can cancel, so this rule only applies when you have canceled all possible values in the denominator. So remember, we did that canceling before not so long ago, and that did not create an asymptote, it created a hole in the domain. So that is not an asymptote. Even though it's a discontinuity, it is a hole in the domain, but it's not an asymptote. So once again, it's like x squared minus 1 over x minus 1. I cancel x minus 1, and I end up with this. Okay. Now, let's see if you remember from not long time ago. What if I am to? Oh, let's just look at this function first. What can you say about horizontal asymptotes? Well, usually there's only one. So is there a horizontal asymptote? Why not?
And like which function?
The function that we have, yeah, same.
It might be 0
Yeah, it is 0. So how do you know?
because as x is the infinity, y
Yeah.
goes to
Y goes to 0, and do you remember, so how did you do the algebra here?
just know that x squared is bigger than 1.
That's right. That's right. It's a rational function. Remember, we did it with sequences. You compare the degrees of polynomials in the numerator and denominator. Which one is larger, controls it. Okay, so that technique applies entirely to this problem. And even here, this is especially simple because numerator is 1 and denominator is clearly high dimensional polynomial. So you know that it's going to end up at what? Why did I write 0 here? This is y equals 0. The horizontal asymptote is y equals 0. And we just evaluated doing comparison. It might be slightly more complicated in when the degrees are the same, and the thing to worry about is, in fact, how differently you treat the function when you're looking at the vertical and horizontal asymptotes. So we factor, in the first example, we factor the numerator for the horizontal asymptote, for the vertical asymptote, right? That's what we did over here. But if we are to do horizontal, it is actually better and easier if it is not factored. So for example, I have 2x squared minus 7x plus 17, okay? So the fact that it's not factored makes it easier to see the leading terms. In seeing the leading terms is all you need to do to find the limit. So what's the limit?
3 halves.
3 halves as x goes to plus infinity or minus infinity for that matter. So, and then once you have this limit, then y equals 3 halves is a horizontal asymptote. Okay. Okay, so that's an overview of asymptotes. Polynomials have none. Exponential function has 1. And a rule of thumb is that rational functions have asymptotes, and it is one horizontal asymptote. It's the same on left and on right. Okay, so 1 over x has only one horizontal asymptote, even though two limits, right? There is one limit plus infinity, the other minus infinity. If it is a rational function, we don't have to worry about it, whether it's plus or minus. With exponential function, remember it has two different horizontal asymptotes. Or rather, it has horizontal asymptote on one side and no asymptote on the other. Where is it? Here it is. There is no asymptote on the right. Okay. Trig function, arctangent. Where is it? Where is it? Okay. Next page. How do I move to the next page? Arctangent, same story. As you can see, different asymptotes, similar story, different asymptotes on left and on right. But for rational functions, that's not as problematic. Arctangent, and well, let me give actually one example of a vertical asymptote. Is kind of interesting. Because it is in the field of physics. Okay, we're here. Okay, Newton's law of gravity. Well, actually, we could take two things of Newton's. Newton's law of cooling and Newton's law of gravity. It is kind of interesting to put them side by side or change. So Newton's law of cooling is that he usually mostly used words, but but if we put it in the more familiar terms, we would say that the temperature, so the room temperature, no, the temperature of an object is exponentially approaching the room temperature. Okay? In other words, t of x is time, is equal to t naught plus e, well, some coefficient here, say a negative x. Okay? So this is room temperature, t naught. T is the temperature of an object. So temperature of an object is this. Room temperature is that, T naught. And this is the exponential part. So as you can see, the difference between the temperature of the room and the temperature of, say, a cup of coffee that we brought in is going down as an exponential function. Okay? So, okay, that's pretty much what he said, and that's what we wrote. And then if we want to describe it in terms of asymptotes, what do we say? So what do we say about this function t of x?
It will be you'll only have one asymptote.
Yeah.
And it will be t of
What?
plus.
No.
Or would it just be t of o?
T naught. T naught is the horizontal asymptote. Okay, looking like this. So it is very predictable. So either you bring a cup of coffee into this, then it will behave like this. Okay, or you bring a piece of ice in this, then it will behave like that. Either two possibilities are taken care of, whether A is positive or negative. Okay, so that's the Newton's law of cooling. Newton's law of gravity. Anyone remembers anything about it?
It's 9.8 meters per second. It's weird.
No, you're talking. That's not that one. I'm talking about on the planetary scale. So the gravity.
Must come down.
What?
Objects that go up must come down.
No. It's not. So once again, you're thinking about the object dropping on the surface of the Earth. I'm talking about the sun and the Earth attracting each other. It was his discovery that to say that it is actually the same thing. That's quite a discovery. But
Mass?
the masses are involved. Yes. So the gravity is a force.
But does this one have energy in it?
What?
Does this one have energy in it too?
No, just the is the force proportional to either of the masses, and so the bigger the object, the harder it pulls the other object. Okay, but it's also how does it change? It depends on the distance between the two bodies. Remember what the dependence is? I mean, if you heard, it is inversely proportional to the square of the distance. Between them. Okay, so this is what it's written. F is equal to some gravitational constant, m, two masses, and 1 over r squared. Okay, so then if you try to, so that's the function. You can think of it as a function of of the distance, because gravitational constant is a constant. We can assume that masses are fixed as well. So it's a function that entirely depends on the distance. It's all applicable to Sun versus the Earth, or the Earth versus the Moon, or Moon versus the spacecraft. It's all equally applicable to all of these. Okay, so it means that it could be, the spacecraft could be moving through this, and it will be pulled towards by any celestial body. Okay, so then if we study it as a function, what can we say? Asymptote-wise. So can you put it in the language of asymptotes, or you said that it's in what's the limit?
The limit is 0.
The limit is 0 at.
As R goes to infinity.
Yeah. So in other words, y equals 0 is a horizontal asymptote. Okay, to begin with, any vertical asymptotes? Well, yeah, that's right. So r equals 0 is a vertical asymptote. So the graph roughly looks like this. Well, very simply, it's almost like 1OX, except it's tighter. It goes towards the origin faster. That's all. So that's what it looks like. R, and this is y being so this is my force as it depends on time. This might sound strange. The vertical asymptote seems strange, and that part of the graph does not seem plausible, because there's no way you reach the infinite force. But it's actually not the distance between them, but rather the distance between the centers of mass of the two objects. So centers of mass. So it means that right now, the distance from us to the Earth is actually quite large. Not to the Earth, but rather to that location, which is referred to in the gravitational law. It is the center of the Earth is that, and that's how we measure the distance. Which still, that if you look at it, it suggests if we take it for granted, it means that if we drill the hole through the Earth, then the gravitation in the middle will be infinite, which is not true. The gravity is actually not increasing as we drill and we go deeper. It actually decreases, and it is the gravity at, well, the movie was Total Recall, the last version. So they actually went from like London to Australia through the center of the Earth, and there is in the middle there was a weightlessness.
It's all lava and stuff.
Yeah. So there is no the gravity is 0 for a simple reason. If you think about it, if you're right in the middle, the gravity that pulls you to the right is canceled by the gravity pulling to the left, and so on. Okay, so the gravity is actually canceling out, and the closer you are to the center of the Earth, the more canceling happening, and then the gravity is smaller and smaller. So the reality is actually, that Newton knew that as well. So that's just a simplified version, but he knew that it looks like this in reality. In reality, the gravity goes down to 0.
Flat Earth. I swear.
Well, that's a question. Is an interesting. What is, if we assume the Newton's law of gravity? What would the gravity feel like if the Earth was flat?
It would be weaker towards the edges. It'd either be weaker or stronger than one.
I'm not sure.
There'd definitely be a difference.
Yeah, definitely. I actually think, well, first of all, it's like a coin, okay, so it's like a coin, and then you can actually stand on the edge of the coin, and that will be the...
Well, he thinks Antarctica is like there's this great big wall in Antarctica that the U.S. government's like keeping us from seeing.
Well, try to prove it's not true. Try to prove it. Now
I'm
look
like,
at the
let's get a GoPro,
look out of the window.
send it out in space. I'm
No,
already
no, that's too complicated. Well, that's if you were talking to your grandmother or whoever, you look at out of the window and point out something that proves that the Earth is not flat. Try it.
Well, a shadow. You can do a shadow like that. If
You
you're
do what?
like- because the sun will cast a slightly different angle if they're in two different places. That's how they proved it.
Well, that takes a travel. Yes, it was like 2,000 years ago, but you have to travel quite a big distance to actually take and have a synced clocks, so you're measuring at the same time, and to show that the two sticks standing in two different locations, maybe at least 100 miles away to see the difference or so, and they cast different shadows. But that nowadays you can call on the phone, and stick of the same stick, pencil, give it to a friend. Okay, that sounds like a plan. Give that to your grandmother, and a pencil, put it on the ground. Okay, and then you have your whatever face time thing. You show you're located elsewhere at the same exact time, and you're measuring the shadow over the phone, and you can see that it is there different. That would prove pretty well that it is not flat. It only proves that it's not flat, but it does not prove. So it means that there is some kind of curvature. But well, there is still possibility. What you're thinking about is that the sun is large in the sense that all the rays of light go parallel to each other. And it is true, we know that. But imagine that the sun is actually like a street light, and it goes like this. And then the argument is out of the window, unfortunately. So even though it works.
It really underestimates how big the Earth is.
Right. Well.
That's the whole thing.
Oh, okay.
Sounds like Christopher Columbus.
He's like.
Yeah, that's right. That's right. Well, he maybe he forgot. Well, he was wrong by about size of 3. So I'm thinking maybe he forgot to put pi somewhere.
Columbus thought that the Earth was pear-shaped, not a globe. So he thought it would be simple to travel all the way around the world. That's why he thought that they could do it. Like people thought about it before. They knew the Earth was round back then, but he thought that it was much smaller in diameter. So he thought he could make it to India easily.
Yeah, that's why I'm thinking it's pi. He forgot to put the pi where it belongs. When you pi r squared or pi r, 2 pi r, and if you miss pi, then the Earth is much smaller, and then you can just cross. He thought it was like 1,000 miles to reach China from Spain. So it's certainly a very, very big miscalculation. Okay, so we'll meet next week then.